Hi everyone. Today we're going to study definition, terms, and common difference of arithmetic sequences. First, let us define arithmetic sequence. An arithmetic sequence is a sequence that has the property that the difference between any two consecutive terms is a constant. This constant is called the common difference. If a sub 1 is the first term of an arithmetic sequence and d is the common difference, the sequence will be like this. A sub n equals, the elements are a sub 1 as the first term. The second term is a sub 1 plus d. The third term is a sub 1 plus 2d. The fourth term is a sub 1 plus 3d. So on and so forth. We may also write arithmetic sequence in simpler form like this. The first term is a sub 1. The second term is a sub 2. Third term is a sub 3. Fourth term is a sub 4. So on and so forth. Let's have an example of an arithmetic sequence. First term is 1. Second term is 4. Third term is 7. Fourth term is 10. So on and so forth. Or we may write a sub 1 is 1, a sub 2 is 4, a sub 3 is 7, a sub 4 is 10. For the common difference, we may compute this using the formula a sub n minus a sub n minus 1. This is difference of any two consecutive terms. So it's like a sub 2 minus a sub 1, or a sub 3 minus a sub 2, or it can be a sub 4 minus a sub 3, and the difference must be common. As an example, we may show that a sub 4 minus a sub 3, and this is 10 minus 7, and the answer is 3. The common difference helps us also to provide the next term after 10, and that is a sub 5, which is 10 plus the common difference 3 is equal to 13. So on and so forth. So we say, once a sub n is known, next term is derived by adding d, the common difference, to it. Let's have more sample problems. Sample problem 1. Write the first 6 terms of the arithmetic sequence with a sub 1 equals 3. This is the first term. And common difference d equals 2. Let us write the general form, and it is written here. Since we need 6 terms, we may write a sub 1, a sub 2, up to a sub 6. In the problem, a sub 1 is already given, which is 3. So we may substitute this value for the a sub 1 in our sequence. Next, we know that next term is derived by adding d to the previous term. So the a sub 2 is equal to a sub 1 plus d, and that is 3, that is the first term, plus 2, the common difference. and the answer is 5. And this number 5, we will substitute to a sub 2 in our sequence here. So for a sub 3, that is equal to a sub 2 plus d, and a sub 4 equals a sub 3 plus d, a sub 5 equals a sub 4 plus d, and a sub 6 equals a sub 5 plus d. So we have this a sub 3 means the 5, which is a sub 2 plus d, is equal to 7. And for a sub 4, that is 7 plus 2, which is 9. A sub 5 is 9 plus 2, which is 11. A sub 6 is 11 plus 2 and equals 13. So these 4 values we will substitute in our sequence here. So the first 6 terms of the arithmetic sequence are 3, 5, 7, 9, 11, and 13. This is our final answer. Let us have example 2. Write the first 5 terms of the arithmetic sequence with a sub 1 equals 17 and d equals negative 3. We need 5 terms, so we write here the general form of arithmetic sequence with 5 terms. The first term is already given as 17, so we will substitute this value in our sequence. For a sub 2, that is equal to the first term plus the common difference d, and that is 17 plus negative 3, which is equal to 14. And this value we will substitute to a sub 2 in the sequence. For a sub 3, a sub 4, and a sub 5, we will compute by simply adding the common difference to the previous term, respectively. So a sub 3 is 14 plus negative 3, that will give me 11. For a sub 4, that is now 11 plus negative 3 equals 8. A sub 5 is now 8 plus negative 3, which is equal to 5. So these values here we will substitute to our sequence. So the first 5 terms of the arithmetic sequence with a sub 1 equals 17 and common difference equals negative 3 are 17, 14, 11, 8, and 5. This is our final answer. Let us have sample problem 3. Is each sequence arithmetic? If so, find a common difference. We have problems A and B here. Let's begin with the sequence A. We can see here that the first term is 1, second term is 2, third term is 4, fourth term is 8, fifth term is 16. In order for us to prove that this is an arithmetic sequence, the difference of 2 consecutive terms must be common. So it means a sub 2 minus a sub 1 is equal to 2 minus 1 equals 1. A sub 3 minus a sub 2 equals 4 minus 2, and that is equal to 2. A sub 4 minus a sub 3 equals 8 minus 4 equals 4. A sub 5 minus a sub 4 equals 16 minus 8 equals 8. We can see that the difference is not common for any 2 consecutive terms. So we can conclude that the sequence A is not arithmetic. We will write our answer opposite sequence A. Let us go to sequence B. The first term is -3, second is 1, third term is 5, fourth is 9, fifth term is 13. Again, we will compute for D, and it must be common. A sub 2 minus A sub 1 equals 1 minus -3, and that is equal to 4. A sub 3 minus A sub 2 equals 5 minus 1 equals 4. A sub 4 minus A sub 3 equals 9 minus 5 equals 4. A sub 5 minus A sub 4 equals 13 minus 9 equals 4. We can see that the difference is common and equal to 4. So sequence B is arithmetic. Let us write our answer opposite B, and that is arithmetic, and the common difference is 4. Hi everyone. Today we're going to study definition, terms, and common ratio of a geometric sequence. Let us define geometric sequence. A geometric sequence is one in which any term divided by the previous term is a constant. This constant is called the common ratio, denoted by R, of the sequence. If A sub 1 is the initial term of a geometric sequence and R is the common ratio, the sequence will be like this. The first term is A sub 1. The next term, we will multiply A sub 1 by the common ratio. So we have here A sub 1 times R. For the third term, we will multiply the second term with the common ratio. That's why you see here A sub 1 times R squared. For the fourth term, this third term is again multiplied to the common ratio. So we have A sub 1 R cubed. And this process will continue on and on. So we say that this is our A sub 1, the first term. This is our A sub 2, the second term. This is our A sub 3, the third term. And this is our A sub 4, the fourth term, so on and so forth. Let's have example 1. Check whether the following sequences are geometric. If so, state the common ratio. We have examples A and B here. For example A, the first term is 1, second term is 2, third term is 4, fourth term is 8, fifth term is 16. For us to know if this is a geometric sequence, we must check each pair of consecutive terms. They must have a common ratio. The formula for common ratio R is this: A sub n, this is any term, divided by the preceding term. Let us take two consecutive terms. Let's say R equals A sub 2 over A sub 1. So it is here. Substituting these values, we have now 2 over 1, and we have 2. This is the ratio of a sub 2 and a sub 1. Let's take another pair, let's say a sub 3 over a sub 2, and this is 4 over 2, which is also equal to 2. Let us take another pair, a sub 4 over a sub 3. That is 8 over 4. And simplifying, this is also equal to 2. Let's have the last pair, the a sub 5 over a sub 4. That is 16 over 8, which is also equal to 2. We can see here that the ratio is common. So we can say that this is a geometric sequence, and the ratio, or I should say the common ratio, is 2. Let us have example B. The first term is 48, second term is 12, third term is 4, fourth term is 2. Let us take the first pair, r equals a sub 2 over a sub 1. That is 12 over 48. Simplifying this fraction, we have 1 over 4. Let's take another pair, the a sub 3 over a sub 2. And that is equal to 4 over 12. Simplifying this is equal to 1 over 3. Let's take another pair, the a sub 4 over a sub 3. That is 2 over 4. And the lowest term is 1 over 2. We can see here that the ratio between two consecutive terms are not equal. So we say that this is not a geometric sequence. This is our final answer. Let us have example 2. List the first 4 terms of the geometric sequence with a sub 1 equals 5 and r equals negative 2. Here we have the general picture of a geometric sequence with first 4 terms listed as a sub 1, a sub 2, a sub 3, a sub 4. Now, for our answer, the first term as 5 is now listed in here. For us to find the next term, or the a sub 2, we will multiply the term by r, or the common ratio, to get the next term. It means to say the a sub 2 is equal to this number 5. The first term is multiplied to the common ratio negative 2. So that is 5 times negative 2 is negative 10. This value we will substitute in a sub 2. Now let us find a sub 3. Simply we will multiply this negative 10 to the negative 2, and that is positive 20. Let us substitute the value 20 for a sub 3. Now for a sub 4, we will multiply this a sub 3, which is 20, to negative 2, and we will have the negative 40. We will substitute this negative 40 in here. So we are now complete with our first 4 terms of the required geometric sequence. This is our final answer. Let's have example 3. List the first 5 terms of the geometric sequence with a sub 1 equals 400 and r equals 1/2. Here we have the first 5 terms of the geometric sequence from a sub 1 up to a sub 5. Since 400 is given as the first term, we may substitute now this value in here. Now let us find the next term, a sub 2. Again, we will multiply this 400 to the common ratio, 1/2. So that is 400 times 1/2. That is equal to 200. We can now substitute this 200 for a sub 2. Next, the a sub 3 can be found by multiplying this 200 to the common ratio 1/2. And our answer is 100. Let us substitute this 100 to a sub 3. To get a sub 4, we will multiply this 100 to the common ratio. So that is 100 times 1/2 is 50. This 50 will take the place of our a sub 4 here. Now for a sub 5, 50 times 1/2, that is 25. And this 25 is the value for our a sub 5. We are able to list the first 5 terms of this geometric sequence. This is our final answer. Hi everyone! Today we're going to study recurrence relations. A recurrence relation for a series is an equation that illustrates the relationship between the term a sub n and one or more of the sequence prior terms. When a sequence satisfies the conditions of a recurrence relation, we refer it as solution to the recurrence relation. Example 1. Let a sub n be a sequence that satisfies the recurrence relation a sub n equals a sub n minus 1, then plus 3. For n equals 1, 2, 3, and so on. And suppose that a sub 0 equals 2. What are a sub 1, a sub 2, and a sub 3? Let us write our relation down here, then let us start solving a sub 1. In this a sub 1, our n is equal to 1. Let us modify our formula based on n equals 1. Therefore, a sub 1 equals a sub 0 plus 3. In the problem, given the value of a sub 0, that is 2, we substitute this 2 in the a sub 0. So we have now 2 plus 3, and the sum is 5. This is the value of a sub 1. Let's go to a sub 2. In here, our n is equal to 2. We modify our formula based on n equals 2. Therefore, a sub 2 equals a sub 1 plus 3. The a sub 1 value is derived from our solution here, and that is equal to 5. We substitute this 5 to a sub 1. So we have now 5 plus 3. And the sum is 8. This is the value of a sub 2. We go to a sub 3. In here, our n is equal to 3. Therefore, using our formula, a sub 3 is equal to a sub 2 plus 3. The value of a sub 2 is derived as 8. We substitute this value 8 for a sub 2. So we have 8 plus 3. And the sum is 11. This is the value of a sub 3. Example 2. Let a sub n be a sequence that satisfies the recurrence relation. A sub n equals a sub n minus 1, then minus a sub n minus 2, for n equals 2, 3, 4, and so on. And suppose that a sub 0 equals 3 and a sub 1 equals 5. What are a sub 2 and a sub 3? Let us write our relation down here. Then let us start solving for a sub 2. In here, our n value is 2. So the formula becomes a sub 1 minus a sub 0. In our problem here, given the values for a sub 1 as 5 and a sub 0 as 3, we substitute the corresponding values in our equation. So we have now 5 minus 3, and the difference is 2. This is the value of a sub 2. Then we go to a sub 3. The n value is 3. So the formula becomes a sub 2 minus a sub 1. We have the value of a sub 2 in here, and the a sub 1 is given as 5. We substitute the corresponding values as 2 minus 5, and the difference is negative 3. This is the value of a sub 3. Example 3. Verify whether the sequence a sub n equals negative 1 raised to n power multiplied by 5 is a solution to the recurrence relation a sub n is equal to negative a sub n minus 1, where n is greater than or equal to 1, and a sub 0 equals 5. Our step 1 is to check the initial condition, that is a sub 1. For the sequence, this is our formula. We copy it here. When we have a equals 1, that is a sub 1, this is equal to negative 1 is raised to power 1 times 5. And we can simplify this into negative 5. Then we go to the recurrence relation formula. A sub n is equal to negative of a sub n minus 1. Let us solve the value for a sub 1. And this is equal to the negative of a sub 0. In our problem here, given the value of a sub 0 equals 5, we substitute this 5 in our equation. So we have negative of the 5 and simplify this into negative 5. We can see now that the values of a sub 1 in the sequence and for the recurrence relation are equal. Therefore, let's go to step 2. Plug in the required sequence value to the recurrence relation and derive a sub n. Let's write first the recurrence relation. A sub n equals the negative of a sub n minus 1. Take note that we have here an n minus 1. Then we go for the sequence formula. Using the sequence formula, we will derive the n minus 1 value. So we have this a sub n minus 1 is equal to negative 1 is raised to n minus 1 times 5. Then we will substitute this value into the recurrence relation formula. So we have now this negative of the negative 1 raised to n minus 1 times 5. Let us simplify this equation. Take note that this negative 1 raised to n minus 1 can be written as like this. Negative 1 raised to n all over negative 1. The negative sign here is copied below, and the constant 5 is also copied. This negative and negative in the denominator can be cancelled out into positive. So this becomes negative 1 raised to n all over 1, then times 5. In our fraction, since our denominator is 1, we can cancel this. So it becomes negative 1 raised to n times 5. Notice here that this value is equal to our value of the sequence. So we can write this equal to a sub n. We say that, therefore, the sequence a sub n is equal to negative 1 raised to n times 5 is a solution to the recurrence relation. Today, we're going to study Fibonacci sequence. The Fibonacci sequence f sub 0, f sub 1, f sub 2, and so on is defined by the initial conditions. F sub 0 equals 0, f sub 1 equals 1, and the recurrence relation f sub n equals f sub n minus 1 plus f sub n minus 2. For n is equal to 2, 3, 4, and so on. Example, find the Fibonacci numbers f sub 2, f sub 3, f sub 4, f sub 5, and f sub 6. Let us write the formula or the recurrence relation of Fibonacci numbers. Also, given the initial conditions f sub 0 equals 0, f sub 1 equals 1. Let's begin with f sub 2. Here, our n is equal to 2. So, corresponding to our formula, this is equal to f sub 1 plus f sub 0. Substituting the values, f sub 1 is 1 plus f sub 0 is 0, and the sum is 1. This is f sub 2. Let us go to f sub 3. This is equal to f sub 2 plus f sub 1. The f sub 2 is equal to 1 plus f sub 1 is also equal to 1. So the sum is equal to 2. This value is the f sub 3. Let's go to f sub 4, and this is equal to f sub 3 plus f sub 2. The f sub 3 is equal to 2 plus f sub 2 is equal to 1. So the sum is equal to 3. This is our f sub 4. Now f sub 5. This is equal to f sub 4 plus f sub 3. F sub 4 is 3 plus f sub 3 is 2. So the sum is equal to 5. This is our f sub 5. Then the f sub 6 is equal to f sub 5 plus f sub 4. F sub 5 is 5 plus f sub 4 is 3. So the sum is equal to 8. This is our f sub 6. We are now complete with the values required. I hope you see the pattern for this Fibonacci sequence. And that is, we add the two prior numbers to get the new number. Therefore, the Fibonacci sequence is starting from 0, 1, 1, 2, 3, 5, 8, and so on. Today, we're going to study summations. The sum of terms of a sequence such as a sub 1 plus a sub 2 plus a sub 3 plus up to plus a sub n, this is from the sequence a sub n, can be written in sigma notation as like this. We read this as summation of a sub n from I equals 1 up to n. Or this notation, we read this as summation of a sub n where I is between 1 and n inclusively. The first notation here is the most commonly used. The value of the variable I is referred to as the index of summation. The index of summation traverses every integer from its minimum limit of 1 to its maximum limit of n. The selection of the letter I as the variable was entirely arbitrary. We might have chosen any other letter such as J or K. Let's go to infinite series. Infinite series is the sum of infinitely many terms or numbers. A sub 1 plus a sub 2 plus a sub 3 plus and so on can be written as summation of a sub I, where I equals 1 up to infinity. Let's have example 1. Use summation notation to express the sum of the first 100 terms of the sequence a sub j, where a sub j equals 1 over j, for j equals 1, 2, 3, and so on. We take note that the index or the minimum limit equals 1. The maximum limit equals 100. And the a sub j equals 1 over j. So our answer here is summation of 1 over j from j equals 1 up to 100. Example 2. What is the value summation of j square, where j equals 1 up to 5? For our solution, first we take note that the minimum limit or the index equals 1. The maximum limit equals 5. So, summation of j square from j equals 1 up to 5, we write this into 1 square plus 2 square plus 3 square plus 4 square plus 5 square. Simplifying the terms, we have now 1 plus 4 plus 9 plus 16 plus 25. And the total is 55. This is the final answer. Example 3. What is the value of summation of the quantity -1 is raised to k, where k equals 4 up to 8. First, we take note that the minimum limit equals 4, while the maximum limit equals 8. Summation of this quantity -1 that is raised to k, where k equals 4 up to 8, we now expand into -1 raised to power 4 plus -1 raised to 5 plus -1 raised to 6 plus -1 raised to 7 plus -1 raised to 8. Simplifying this, for those -1 that is raised to even powers, that will be +1, while remains to be -1 for those with odd powers. So we have now this 1 minus 1 plus 1 minus 1 plus 1. We simplify this into +1. This is the final answer. Today, we're going to study double summations. This is the rule. To get the value of the double summations, you must first determine the value of the inner sum. Then, determine the value of the outer sum. Example 1. Find the value of these double summations. Let us copy our problem here. The rule says, let us evaluate the inner summation first. This is the inner summation. We're going to expand the inner summation. It means we're going to replace the variable j with the numbers from 1 to 3. So we have now I plus 2i plus 3i. The outer summation we will just copy. Then let us simplify. This I plus 2i plus 3i becomes 6i. Now we have a single summation. And this is now summation of 6i, where I equals 1 up to 4. When we expand this, we will have this 6 times 1 plus 6 times 2 plus 6 times 3 plus 6 times 4. We simplify each of the products. We have now 6 plus 12 plus 18 plus 24. And the final answer is 60. This is the value of the double sums. Example 2. Compute the double sums. This is our problem now. We copy the double sums here. Then let us evaluate the inner summation. This is the inner summation. We're going to expand this, which means we're going to replace that variable j with numbers from 1 to 3. So we have now I plus 1 plus the quantity I plus 2 plus the quantity I plus 3. Let us remove the grouping symbols and combine terms. We will copy again the outer summation, that is from I equals 1 up to 2. We simplified these expressions into 3i plus 6. Then let us evaluate this single summation. We're going to replace I by numbers from 1 to 2. So we have now this 3 times 1 plus 6 plus the group 3 times 2 plus 6. When we simplify each group, it becomes 9 for the first group plus the second group is 12. 9 plus 12 is 21. This is the value of the double sums. Today, we're going to study partial sums. A partial sum, denoted by S sub n, is a sum that is calculated for only a portion of the entire sequence. A partial sum that can be calculated from an infinite series is the sum of finite number of consecutive terms that follow the first term. Example, find the first 4 partial sums of the infinite sequence a sub n equals 1 over 2 raised to n. Let us write the terms of the sequence. These are 1/2, 1/4, 1/8, and so on. The S sub n represents the sum of the first n terms of the sequence. Let's begin with S sub 1. This is equal to the first term itself, 1/2. For S sub 2, we're going to add the first two terms, 1/2 plus 1/4, and this is equal to 3/4. The S sub 3 is the sum of the first three terms, 1/2 plus 1/4 plus 1/8, and the total is 7 over 8. For the S sub 4, we will now write the sum of the four terms, 1/2 plus 1/4 plus 1/8 plus 1 over 16, and the sum is 15 over 16. These are the values of the first 4 partial sums. Take note, each of the results is a partial sum of the series, summation of 1 over 2 raised to n, where n equals 1 up to infinity. Today, we're going to study some summation formulas. Let's begin with the first summation. We have the summation of a times r raised to k, where k here equals 0 up to n. There's one condition that r is not equal to 0. And the closed form will be like this. In here, r should not be equal to 1. Next, summation of k, where k equals 1 up to n. The value is n times the quantity n plus 1, all over 2. Next, summation of k square, where k equals 1 up to n. The value is n times the quantity n plus 1 times the quantity 2n plus 1, all over 6. Summation of k cube, where k equals 1 up to n. This is the closed form. This is similar to our formula in here, except there is power 2 in this closed form. Next is summation of x raised to k, where k equals 0 up to infinity, given that the absolute value of x is less than 1. And the form is 1 over 1 minus x. summation of k times x that is raised to k minus 1, where k equals 1 up to infinity. In here, the absolute value of x is less than 1. And the value is 1 over the quantity 1 minus x is raised to power 2. Let us see some examples. Example 1, find the summation of k squared, where k equals 50 up to 100. Take note that summation of k squared, where k equals 1 up to 100, is equal to the two summations here. The first is summation of k squared, where k equals 1 up to 49, plus summation of k squared, where k equals 50 up to 100. In our problem here, it refers to this summation. With this equation, if we want to solve for this summation, we're going to transpose this first summation to the left side. So we will have like this. Summation of k squared, where k equals 50 up to 100, and that is our problem, is equal now to summation of k squared, where k equals 1 up to 100, minus summation of k squared, where k equals 1 up to 49. We're going to use one of our formula in our list a while ago, and that is summation of k squared, where k equals 1 up to n, and this is the value. In our first summation, the n is 100. So we will have now this 100 times the quantity 100 plus 1 times 2 times 100 plus 1 all over 6 minus the second summation. Our n here is 49. So we write here 49 times the quantity 49 plus 1 times the quantity 2 times 49 plus 1 all over 6. We simplify the numerators respectively into 100 times 101 times 201, and this is all over 6, minus the second numerator will be 49 times 50 times 99 all over 6. Simplifying the fractions, we will have now this first fraction equivalent to 338,350 minus the second fraction is equal to 40,425. And the difference is 297,925. This is the final answer. Example 2, find the value of summation of the quantity k times k minus 1 times k plus 1, where k equals 1 up to 10. We copy our problem down here, and the first thing that we will do is to simplify our function. Let's begin by multiplying this k minus 1 times k plus 1. So we will have this k squared minus 1. And then this k outside, we will distribute to each of the terms inside the grouping symbol. We have now this summation of k cubed minus k, where k equals 1 up to 10. From here, we're going to distribute the summation notation into k cubed and then with the minus k respectively. So we will have like this, summation of k cubed, where k equals 1 up to 10, minus summation of k, where k equals 1 up to 10. In our list of formulas a while ago, we have like this. We're going to substitute the corresponding values respectively. Then let us evaluate respectively. We have now this 10 times 11 over 2, and this is raised to power 2, minus 10 times 11 over 2. We simplify each into 55 square minus 55. This 55 square is equivalent to 3025. Minus 55, the difference is now 2970. This is the final answer. I hope you learned something from this video. See you again next time.